Hello, so we continue with knot theory, operator algebras, and a little bit of physics. Adam, again, the floor and the Zoom is yours. Take it away.
Thank you. So last time I defined the Jones polynomial. We discussed the motivation of Jones leading his work on Neumann algebras leading to it. And then I started telling you about another construction of the Jones polynomial. So let me come back to this. It's due to Kaufman. It involves framed links. So just as a reminder, framed link was just an embedding of annuli into some three-dimensional manifold M. And so really, you can think of them as unframed links with some tangent, well, some actually transverse vector field, which is called a framing. And so these are really links. So links plus framing, yes. And framing on each component can be classified by integer. So the Rademeister moves, so they again can be given by diagrams, represented by diagrams, traditionally with so-called blackboard framing or Zoom board framing, and subject to Rademeister moves. So I'm going to write it here, given by.
I'm very happy because this is another incarnation of a digit 6. 6 already played the role of sigma and of 6, of course, and now it also plays the role of G.
Oh.
In the very same lecture, where sigma referred to 6, G was like a 9.
Yeah,
you remember?
Exactly,
Yeah.
but it was lowercase G was like 9, yes.
So they are given by diagrams and up to relations, where the first one is framed Rademeister relation, and it can be drawn like that. So you have positive and negative kink of sorts here, and then the other two are just the standard relations, R2 and R3. So one was like that.
But these are only cores of this fragment, these ribbons. Okay.
These are relations for diagrams of framed links.
So framing is not indicated here.
Well, as I said, I'm going to use the Zoom board notation convention, which means that framing is always parallel to the board.
Okay.
That's why we don't see it.
Yes.
And then, so it's not a big of a deviation from classical knot theory. And then Kaufman proved the following. It turns out that those framed links are very useful for what he did. And that there exists unique and there is unique bracket polynomial going from framed links to Laurent polynomials in Z, well, with Z coefficients. This is supposed to be 1, not 7. And satisfying the following relations.
Wait, when you say a bracket is a bracket which has only one argument, right? Ah, it's two arguments.
Blank.
No, one argument.
One, so one or two?
One argument.
One argument.
Yes, which is the frame.
Because it's the comma, which confuses me.
So
Okay.
it satisfies the following properties. So first of all, we have a skein relation, which says that whenever you see a crossing in a diagram, you can replace it by two types of smoothings. Take their brackets. And there will be a relation like that. Between those three polynomials. So this is called Kaufman bracket scalar relation. And then the second relation says that if you have a link with trivial component disconnected from it, disconnected meaning untied, unlinked with L, then this is the same as L times delta. And delta, it's a bit unexpected thing, but it's minus a squared minus a to negative second. It's weird, but it's the only. So first of all, I would say this is a very natural relation, the first one, and to consider. And this one turns out, this value of delta turns out to be the only possible one to make this theorem work, to make this invariant exist.
Sorry, particularly if we take only this unknown, then we get that the bracket of this unknown is just delta, yes?
Yes.
So this
Yes.
link L would be empty, yes?
That's right. That's a good point.
Class of L of 0.
That's a good point. You're right. And I'm going to write it like this. Yeah, so this is called the Kaufman bracket. And how do we prove that? Frankly,
First of all, these frame things are not oriented. In opposite to John's scalar relation.
that's correct. And to me, it's a pleasure to prove this theorem. Yeah, so how does this work? Well, first of all, a state, let's define a state. A state of D is a smoothing of all crossings. So a diagram with n crossings will have two to power n states. And and notice that by this relation we can eliminate all the crossings until we get states. And we have a sum here, but if we repeat this process n times when n is number of crossings, you will get a state sum formula, which says that D is a sum over all states. States S. Okay. I hope this is readable. States S. And so in the process of getting from a diagram to a state, we're going to be acquiring either A or A inverse. So we will get A to certain power. What's the power? Will be P of S minus M of S. I wish I could just throw this board like halfway, but I can't. So I just need to use small letters here. Maybe I'm going to erase something here.
And erase and go to the next one.
Well, I don't want to rewrite this, so I'm going to erase part here.
I mean, experienced people know how to frame a piece of writing on this whiteboard and move it up or down.
Yes,
It is possible.
you're right.
Using select.
Yes.
Absolutely. Let me practice that.
And the whole, yeah.
Now I should do copy, no?
I don't know. I told the experienced people.
Now,
I should be able to move it, but
try to move it.
Can I move to the?
No. Use the.
now you mark using and move it
How
out.
can I move to the new board?
Well, you always move to the new.
Then you have to copy.
Can I like paste it? No.
No.
Select text.
Okay, let's not waste time for this. These are the things you have to try to figure out before your lecture.
All right, so P of S. Okay, so first of all, will be some power of A. I'm going to repeat this process, this equation, this relation for all crossings. We're going to have 2 to n terms, because each crossing is 2 of them. We'll have a power of A, where P is what? It's the number of positive smoothings.
So smoothings are these moves, right?
Positive smoothings. This is a smoothing, replacement of this crossing by this type of thing. It's a smoothing.
Yeah. And you have positive, negative, and what is the last?
Yeah, so this one is positive,
Mhm.
and the second one will be, of course, negative.
Yes.
Well, in retrospect, this should be n, not m. And then, what do you get the bracket of at the end? Well, a state. And what is a state? A state is a bunch of loops. And what's the Kaufman bracket of a bunch of loops? Well, it's going to be a power of delta, because each of those loops can be eliminated and replaced by delta. So there will be a delta here to power. I will write this way, and this means the number of loops, number of components in a state, which is a bunch of loops. Like if there's one crossing, suppose there's one crossing, what does it say? Well, it means that it's going to be a sum of 2 terms. It will be A times value of one state, which is a bunch of loops, plus A inverse times value of another state, which is also a bunch of loops. What is the bracket of a bunch of loops? It was delta to a certain power, number of components.
And why smoothing of one crossing is a loop?
Well, if you have one crossing, then smoothing of that one.
Because you're talking links all the time. So, okay, so yes. Mhm.
This means that there is a link in the background.
You write a crossing, but it's just a local picture.
That's right.
Okay.
That's the nature of the word skein. It's a skein relation, which will be important. Too complicated. This is the Kaufman bracket skein relation. So we have a state sum formula like that. Okay, so in particular, it's implied by this formulas. In particular, the bracket is unique if it exists. How do we prove it exists? Well, we just need to verify there's 3 Rademeister moves, and it's really simple. So existence well, but let's look at second Rademeister move, for example. So we want to check if this bracket is equal to this bracket. And what's that? Well, you can write it down as a square, and we'll do the 2 a smoothings or positive smoothings.
You can draw a red circle around crossing you are interested in.
That's true, but I am already doing 2 at the same time. So these are both A smoothings plus I'm going to do negative smoothings. So
No, this calculation allows you to do one smoothing for one, so two smoothings for one crossing. So you
I know, I kind of
did it twice.
did it twice and I
Yeah.
challenge it. Okay,
Not allowed by the relation.
all right. Well, I think it's okay to use it twice, but maybe it's too fast.
Instead of one line, you should
Okay,
two lines.
all right, we'll do that. So,
Choose your crossing.
With a red circle.
sure. Why doesn't disappear? Who knows? All right.
Go.
So this will, I'm going to do this crossing first. I employ here the Picasso style of not theory things. Not necessarily connected. And then we will do this one. So we agree with this one. And then how much is this one? Well, I'm going to be a square. Okay, yeah, let's do a square. So now it will be like this. And then it's going to be
Yes.
like this. Okay.
Okay.
Who knows what happened here?
So this A minus means A to minus one. Above.
We agree, and then there will be this term.
Yeah, if you could add one in the.
Yes, I will add one. You know, this is interesting calculation in its own. So I will do it here. I'm going to turn this 90 degrees.
But I'm confused, where is the equality sign?
Sorry?
Where are the equality signs?
Yeah,
Below.
this is the left-hand side. So equality is from here to this line and to this line.
Okay.
So maybe writing this on the right hand side after this
Okay.
this mark, it was too early. You don't know what combination of this. No. After you have equality with a question mark.
That's
Above.
okay, sure, yeah.
You don't know what
Sure.
yet. What it, no. Above.
Yes, what about it?
You don't know if this consists of.
That's why I wrote question mark.
Yes, so you should erase what you wrote after this question mark because you don't know what combination you get. Yet.
Okay, I want that.
Confused. You are not proving this equality for sure.
Okay. Well, no, I'm proving this equality for sure.
Really?
Yeah.
Yes.
So it's like starting
Okay.
to the left and
I still go.
Okay.
you would like to claim what is on the right.
What I would
Okay.
suggest, Adam, take this question mark and this equality and the whole picture in some red circle, and we know that this is what we are focusing on, and then just run the calculation down. You put text.
If I understand,
Not text. Why did you put text? I don't understand why you switched.
no, it wasn't.
Yes, exactly. And then we know that is, and now I know that the equalities run down. But I would write them. I see nothing wrong with writing equality signs.
Okay, now I'm going to do high tech. We'll see what happens. Oh, very nice. And let's go with that.
Wonderful. Yes.
Last.
Last, okay, but now I want to do this calculation because it's of interest in its own. I want to understand what's that. Well, how much is that? And well, you can do A. And then what do you have? You have one arc with delta, because you will look, and then you have a smoothing, which gives you one arc. And of course, this is A inverse. So this is how much? Well, this is a.
So instead of straightening these strings, you could draw the shape, suggesting what result.
I mean, if I understand what you say is.
Yeah, one arc and one.
That's what you mean?
That's the same thing.
Yeah, but you omitted this one relation. So in first step, you are producing this arc and a node in the loop. And then you are applying this condition with delta.
Yes.
It's one relation.
Yeah.
Okay. In the second is A minus, and this is smoothing, producing something like this.
I see what you, okay, yes.
So you omitted two things. So people looking at this first time in their lives, yeah.
Okay. Okay, and then what do we have here? Well, we have minus A to the third. Sorry, this is too bad. Minus A to the third. Minus A. No. To the minus first, yes. Plus A to minus first bracket. Okay, and what's that? This is minus A to the third power. So this is just on its own. It shows that we really need to deal with framings, otherwise clearly there will be invariant fix. And so what do we put here? Well, we put minus A to the third. And times this business. Now we have a wonderful cancellation of these two terms. And we get the desired property, invariance of the second Rademeister move. So it's a child's play. You know, and the same proof, we use similar proof for the third Rademeister move and the first frame for the Meister move. Well, basically, when you have a negative at the other crossing here, then you get the same, but the inverse of this coefficient. All right, so that's the proof. And
Wait, let's go back to the statement. I'm completely confused. So what did we prove? Why is the
Invariance with respect to the first.
we define the bracket for framed link diagrams.
okay?
And this proves that this bracket is preserved by the second Rademeister move.
Okay,
I use scalar relations to
Yes.
prove that this is equal to
Yes.
that. And the same way you prove the
yes,
other two moves.
yes.
So it is a proof that this formula given before is well-defined invariant of this link.
Yeah,
But why is it enough to check it just for Rademeister moves?
well, you know, diagrams of links are not interesting. What is interesting is quantities which are defined for diagrams which are preserved by Rademeister moves, because these are invariants of links. Links are much more interesting than diagrams of links.
So we are thinking up to.
Okay, so this equivalence class up to Rademeister moves is really gives you links.
Yes.
Okay, so I somehow escaped.
Yeah.
And why did, that's why it's called existent, because you proved that it's well defined, okay. Okay, thank you, yes,
So this proves that this is well defined.
yeah, I've got it.
So we finished the theorem. As you can see, the proof is really elementary, but very clever. It's sometimes there's nobody there to try it before, even though it's so simple. I guess nobody believed that such a simple construction can work until Jones came. So
This is Kaufman.
that's right. Kaufman did it, but only inspired by Jones.
Sorry, somehow from this calculation about the existence, one can extract that the value of this delta must be a2 minus a squared plus a2 minus.
Yes,
Yeah.
because if you change this value, you can see that.
So this is responsible for this cancellation, yes?
Right.
Okay.
So this is for framed unoriented links. However, if you have now, so I will do QED here. However, if you have oriented unframed diagram or unframed link, then you can normalize this invariant to invariant of those oriented unframed links. How to do that? Well, so let D be a diagram of oriented unframed link. And then to do this normalization, as you can expect, we'll get to Jones polynomial in a moment. To do this normalization, we need to consider the right, the right W of D, which by definition is a sum of crossing signs. Of D, and so there's a standard convention about signs. Each crossing either looks like this is plus, or like that, and that is minus. Yes, so is it clear that there are only two types? I mean, if you do, what's happened here? If you do, well, this type, then of course you can just rotate it and it's minus again. And so you do this, and then I want to consider this quantity now, minus a to the third free WD, and then I'm going to do the bracket D. So, if I have a diagram, so I have bracket for diagram, so this makes sense.
Is it good writing of this rice? It should be WRITATH.
Yeah. You're right. I apologize for that. Yes, exactly. Right. Yes, sorry, thank you. So I want to consider this quantity. Now, what happens when, well, first of all, it's invariant under second and third order Meister moves, because second and third order Meister moves don't change the right. Second move adds plus positive and negative crossing, and the third one doesn't change the crossings. It's crossing lines. What happens on the first order Meister move? Well, D is going to be multiplied by this factor, but also the right changes, because if you orient it, no matter how you orient it, this will be a positive, right? Positive crossing. So, and so we need minus here. We need minus here. So now adding a positive kink like that will multiply this value by a multiplicative factor, but it will also multiply, will change this factor by the opposite. So this will stay invariant under the first Rademeister move. So this is an invariant of an oriented link, unframed link, right? So there's a theorem which is not difficult to prove. It's part of what Kaufman did, that this is really the Jones polynomial of D, or link represented by D.
Again, I'm confused. So this minus 8 to this power minus 3w of d bracket d, this is what? What is it? Ah, now I know the answer. No. I mean, I missed this equality. Okay. Mm-hmm.
Right, so this defines
Corrected Kaufman bracket.
Wait, but who was first, Kaufman or
no,
Jones?
no. Jones was first. Sometimes it takes complicated work to extract really the main idea and make it simple. So, but Kaufman did it within 2 years from Jones. Right, so now I want to consider a generalization of this construction for other three-dimensional manifolds. And this will lead to some interesting mathematics. This generalization is called schema modules. Well, let's do it. So let M be a three-dimensional manifold, and I only require that it is oriented,
Not compact.
not necessarily compact. Frankly, I don't even need it to be oriented, but the theory is not maybe very interesting. It's not. And so I want to consider all framed links in it. Including, I want to include a link of 0 components, which is the empty set. And now I want to take a ring of coefficients, and this ring will be commutative from this is with identity and with some specified invertible element A in it. And now the Kaufman bracket K module of M with coefficients in R. Hopefully this is readable. Is the following. Well, first of all, we write it this way. And this is going to be the space of linear combinations of framed links. I'm going to take this infinite dimensional free module over R and quotient it in a formal way by the scalar relations, the Kaufman bracket scalar relations. So, okay, I think I suspect I will face resistance to this.
Difference.
Yes, exactly. Generated by that, and generated by relation which says that if you have unlinked component from L, and this is really the same as delta times L. Okay, so this is a strange animal. What are its elements? Linear combinations, formal linear combinations of links, like 2 plus a to 7th times, I don't know, Hopf link. But that Hopf link may sit in this manifold in some interesting way. Plus, you know, maybe 15a and not, but no, then there's some hole in this manifold. Something like this is called a skein. So why do we care about this? Well, first of all, let me say a few basic things. So when the context is clear, I'm going to write it like S of M comma R or S of M if the coefficients are fixed. This was those scheme models, couple of bracket scheme models were introduced by Furayev and Pshititsky. I think their motivation was the following, that a model like this gives you a version of Kaufman bracket for links in any manifold, sort of on the nose, yes? So because now, if you have it, then now you can consider the function.
I'm a bit confused why you have to signify A. Isn't it just a variable in R, a convertible element in R?
That's right, but there are many of those. Often.
But for this module, A is fixed.
That's right.
Okay,
In this way, it can be a formal variable.
okay.
So, you know, for example,
Okay, not a formal variable. It's a variable of R.
Element, yes.
so
Yes, yes.
kind of canonical example to consider, this is actually a good point, is just Laurent polynomials.
Yes, that's what I was thinking about. Exactly, yes.
But it's useful to consider different ones. We will consider different ones for good reason. So, you know, this gives you tautological invariant of links. It's also the bracket. And with a double meaning, you know, you can think of it as Kaufman bracket, but it's really just sending L to its class. You know, what is L is here. And then you can consider its class in the quotient. And now you get some element in some algebraic object. What is that? This is an R module. This is R module.
But in this fact, some property of this Kaufman bracket is used, additivity or linearity, A linearity, R linearity.
I'm not sure what
It's not proved yet.
I think that this bracket is just a notation, it's not Kaufman.
That's right. You can,
It's mimicking Kaufman bracket.
Yeah,
that's right. It's just notation, but it is.
to satisfy these relations must be additive in links.
I don't know what you mean by that. No, I think.
Probably, Tomasz, you
If you
mean
have-
that this definition is just for generators and then you extend.
Yeah, it's extended.
Yes. So probably that's what you meant, yes?
Keep in mind that this,
It's a lab.
yeah, you have unlinked
Set.
two components. And that unlink of two components.
Yeah, but you have combinations.
That's right. Unlink of two components is not a sum of not
Yeah.
not an unlink.
Yeah.
They're different things.
Yes.
So I'm not sure about the
I
additivity.
mean, I think that Tomasz objection is only about this. That you are
So this.
defining on a free model,
Yeah.
yes? So
Yeah, you
it's
can
enough to define.
on the free module satisfying these relations.
Yes, but
Okay.
in order to define something on a free module, it is enough to say how it acts on generators, yes? So this is what is really.
But relations are linear combinations.
Yeah, this is, okay, I see. Yes, this means that we consider.
These are not relations between links. These are relations between.
Yes, so we consider a sub.
Are linear combinations of
Yes,
links.
but
These are
this,
just the generator.
there is no problem, yes?
Yes.
And you don't have any relations in the domain. So in order to well define it, you don't need to check any consistency, yes?
So let me do an example here. So what's the skein module of R3?
Sorry, just a stupid question. How about taking A to be equal to 1 unit in a ring?
You like? You can do it.
Is it somehow more interesting or less interesting?
It's interesting on its own. So both this choice is interesting, and taking a equal 1
Okay.
is also interesting, and taking a equal -1
Yes.
is even more interesting. Yes, and this will lead us also to strange, well, strange, but unexpected mathematics. But let's think about what is.
It was a strange choice of A, because -A is a more important role.
Ah, yeah. It's relation between Kaufman bracket and Jones polynomial, yes?
Yeah, actually, I realized that I forgot about the bookkeeping because this doesn't make sense. You know, if you remember, Jones polynomial is a polynomial in T,
Yes.
and T is going to be A to power -4. And I'm smiling because now I think it's -4, not +4. Yes, so that's how you relate those two. So what is S of R3? Well, first of all, notice that the way it's built of links in R3, each link can be reduced by this relation to the empty one. First of all, to unlink, and then you can eliminate all the loops by producing delta by using this relation. So first of all, I want you to observe that it's going to be really generated by the empty link. Do you guys agree? Because if you give me any link, I'm going to reduce it to a bunch of unlinks, a linear combination of unlinks, and then each of the unlinks will be reduced to the power of delta. So, okay, and so what Kaufman says really well, Kaufman's construction really says that this is the same as R times the empty link. Okay, and then, so what is this construction then? Well, in this case, when you have R3 here, when you have link in R3, what do we get? We get certain element of R. You know, let's consider this ring. What element of R do we get? Well, we get the Kaufman bracket. So for R3, this bracket is the Kaufman bracket.
But what ring?
For R, so Kaufman
R3.
bracket for M equal R3, and this choice of the form of the coefficient ring. So this is a generalization of the Kaufman bracket. So the motivation of, I guess, Torayev and Przydysky was, well, here you can generalize his construction and have an invariant of links in arbitrary three-dimensional manifold, which is only useful for practical purposes if you can compute this thing. And frankly, computing those things is very, very challenging. So first of all,
sorry, Adam. So if I'm not mistaken, so the idea of using this construction for manifolds relies on the fact that these scale relations are local.
yes.
So therefore, you can
R3, yes.
as well as these links in three-dimensional manifold as you did in the case of R3, correct? Yeah.
What do you mean by local? Referring only to choice of the crossing, yes?
Yes.
Getting going.
Yeah.
So let's first make, let me make a bookkeeping.
Anyway, so what is this invariant for the sphere, for S3?
Yeah, so links in S3. What is S3? S3 is R3 with extra point at infinity. And any link can avoid this point at infinity, and any isotopy between links can avoid them. So this is the same here.
And what about M equal to, let's say, sphere, two-dimensional sphere cross R?
Well, this is S3 minus 2 points,
Yes.
and the same argument works. Yes.
Of And it becomes more interesting when S2 is replaced by sub-Riemann surface, for example.
Definitely more interesting, yes.
And this is not trivial.
Correct, yeah, so I think we exhausted the easy cases, which is good. A bookkeeping remark. Ma. And so for any homomorphism of those rings of coefficients and any three-dimensional manifold M, the schema model of M R prime and then H of A, so there's some A here, is just M, schema model of M R A tensor over R with R prime. So that's not a difficult homological algebra. And what it means is that we don't need to, for the sake of computing scale models, we can, it's enough to consider just Laurent polynomials over Z. If you can compute a scale model of this over this ring, then you can compute them over other rings. And now, I want to now, and maybe for that we need another board.
Wait, I have to understand the corollary. Enough for what?
Well, if you understand the lemma says that, okay, so I should explain that this lemma says that if you want to compute it scale model for any ring with specified element A, any such ring is really image of a homomorphism from Laurent polynomials over A.
You're right, of course. Ah, yes, I've got it now.
Therefore, it's enough to consider those.
Yes.
Now I want to, I'm going to continue this theory, but I want to come back now to use what we just discussed to give a simple interpretation of the temporary leap algebra, which we discussed last lecture. So this will be Kaufman approach to temporary leap algebra. And first of all, to do it, I want to consider entangles. So an entangle is an embedding, one manifold embedding into a cube I'm going to take the words, what kind of embedding are we talking about? Well, we're going to project it on a tangle, sorry, on the board. We're going to project on the board, so we'll see a diagram, and it should have n, maybe n would be 3, and points on top and points on the bottom, and then you can draw here anything you like, any one manifold with 3 ends here and 3 ends here. So collection
But you say entangle, so where is n on the right hand side? You have one manifold embedding into Q, which is just.
It's number 3 in this example, for example.
yes.
That's very equal to 3. So why don't you just write Q is equal I to the power n?
Oh, no, Q is
No, no, no,
always
no, no.
three-dimensional. This manifold which is embedded is always one-dimensional, and n is the number of these beginning points.
N is the number,
Dimension is-
the top and bottom.
Okay,
By the way, the number n is equal to 3, but it's an accident.
Yeah,
What's an accident?
Dimension equal to n.
dimension.
Yeah, this is for n, and this is an example of a three tangle because it has three endpoints on top and on the bottom.
this is a number of beginning and
So if you remember the definition of a three braid, it's a special case of a three tangle, but this one is not a three braid, but it's a three tangle. And
Of course, it's not monotonous.
correct. So, and yeah, and also it can have a lot of components, more than three. It has to have at least three components, but it can have more. And then, so let Tn be all entangles. And so I want to consider our Kaufman bracket schema based on tangles, not links. Tangles in Q. So we can maybe do denoted by S again. Q, comma N. You know, I could use R, but well, why not? Okay, I'm going to use R as well because it also depends on R and A. Yes, and it's going to be just again formal space, linear space with basis given by Tn, quotiented by the Kaufman bracket scaling relations. So it's a version of scale model, except in this version, each picture needs to have n endpoints on top and on the bottom.
Sorry, a stupid question. If you do not specify this n, then this tangle is just one particular example of a link, yes?
Well, if you specify n to be 0.
yes.
N must, okay. Okay, you don't have this endpoint. Yeah.
So
I'm really missing in this definition. Entangles are one manifold embedding into Q, comma, where n is blah, blah, blah.
when n is the number of intersection points of a tangle with the top face of the cube.
Yeah.
And which is also the number of intersection of the tangle with the bottom face.
That's what was missing for me.
Generalization of the braid.
That's right. And so it's a space. You know, what kind of model is this? R model. What kind of model is this? Well, first of all, you can see that it's you can resolve all the crossings, and you can see that it's free. And in fact, what's the basis of it? Well, it's going to be a multi curves or arcs. I think I prefer arcs. Connecting, in this case, those 6 points.
And by an arc, you mean something that starts and ends at the same side of your rectangle?
No,
No.
like this one.
Could be.
Well, clearly you cannot have only those because it's the odd number of top ends. Yes, how many of them we have? How many are those? How many multi-arcs are there? Good question for.
Is it n squared?
No,
Something.
no, because that would mean that R can go back to the same point.
Yeah.
And why it cannot?
Well, because it has to be an embedding. Yeah, you don't allow that. And also you can, no, it's not unspread. For other reasons, because in fact you have to specify several arcs. It's actually a much larger number. It's called the Catalan number. So basis, multi-arcs, and there is so dimension of this S is going to be, well, I would note it by Cn and Catalan number.
In fact, dimension of as n or
Sorry?
You should have n also on the left hand
Somewhere-
side.
Yes, and on the
Yes.
left side.
Yes. Yeah, okay. Now everybody knows, I'm just going to leave it like that. This is for specified n. And what else we know about the space? Well, you can concatenate those tangles. If you give me another tangle, n equal 3, together they will form a new tangle. So this makes this Tn into a monoid with identity being, in this case, 3 strands back from. And therefore, this is an algebra, associative algebra, non-commutative algebra. And what are the generators of this algebra? So S, Q, comma, N, R, A is algebra
I'm confused. This is mention of S over what?
over R.
And,
So
and
it's a free module.
Yes.
how do you know it's a free module?
Well,
So that's the proof.
so first of all, you observe
No single cross.
that you can smooth all the crossings and it's generated by things like that. And then you sort of apply the same method as Kaufman did. You know, you can express any tangle in this set, yes? And you can create a state sum formula. The state sum formula will say that this is a sum of elements, combinations of elements like this, in this basis in quotation marks.
Combination is unique.
Well, you don't even know that, but you know that you can do it in a canonical way. And then this canonical way is preserved by Rademeister moves.
Mhm.
And therefore, the state sum is well defined. So we know that this set is spanned by certain this many elements, and then we have isomorphism onto pre-module of this dimension, and this basically proves the deed.
You define for us the Catalan number, please.
Yes. It's a number of multi-arcs.
No. No, it's not a definition. It's
That's my definition.
Number of parentheses.
Choose n divided by n plus 1, something like that.
Very good. But I guarantee you that Catalan didn't define Catalan number this way.
what?
Originally, they were defined in recursive formula. Like summing products of the previous one, different indices, something.
He didn't observe that, so that he didn't start with this question. You know, this doesn't have to be square, yes, it can be disk with 2 endpoints, and you can ask how many matching. Sometimes this is called matchings of 2 endpoints. And yeah.
But I don't see at all why these two numbers are related.
Very good. And there's maybe, there's some proofs, but there's in particular my proof with Józef Przytycki. I recommend my paper on the subject, a combinatorial proof of that fact.
So it's not obvious.
It's not obvious. I mean, if
I was right, it's not a definition, it's a theorem.
well, I mean, okay. Well, I don't think this is either the definition, whatever the definition was. Yes, now we have the identity. So how many we have here for n equal 3? Well, there should be 6 of them if you count carefully. But I claim it's now becoming even more interesting. This is an algebra, non-commutative associative algebra. What are the generators? Well, the generators are, perhaps you can guess, something like that. This is I plus 1, and then you have just straight arcs, and the I can be from 1 to n minus 1. Right, and then, yeah, I don't know. I think maybe I would just leave it for you guys to ponder about this. Well, I mean, if you resolve all the crossings, yes, if you have something like that, then I claim you can make this picture into product of generators. And how do I do that? Well, okay, so I am going to go like this. Okay, so it's going to be product of the first generator and the second generator. Yes. So this is, you can call it GI. And this is going to be G1 times G2. Or G2 times G1, depending on your convention. And so now a theorem, the temporary leap algebra, which you got by considering those projections, E1, E2 in the tower of von Neumann, is isomorphic. If you, the temporary leap algebra for certain n is isomorphic to this algebra for the same n. And in fact, this isomorphism will send to these generators to those of Jones by some linear transformation.
Also denoted by GIs.
Yes, yeah,
So
exactly.
this is about relations between these generators.
Yeah. So the point is that this is very easy to write relations here. You know, what are the relations here? First of all, GI squared is delta GI, so it's like almost an idempotent. Yes, because if you compose it with, you know, if you draw one on top, then it's really GI with this extra loop, which is delta. And then there are what other relations? Well, GI, GJ. It's really the same as GJ, GI for I minus J to be less or equal to 2. I think this is the preferred way of writing it. Yes, because
Yes.
You said less or equal, greater or
greater, sorry, if I say
At least two apart.
yes,
at least.
for obvious reasons, yes. And then there's extra relation, which is about GI plus 1, GI, which is really the same as GI plus 1, GI plus 1.
And what about this triple identity?
Well, I just said it, but I didn't write it. But you,
So I missed it.
okay, so there's one extra identity. I don't want to leave this board, so GI plus 1, GI equals GI plus 1, GI plus 1. Okay, well, we can draw it. What does it say? It says GI followed by GI plus 1, followed by GI, should be equal to GI.
Mhm. If everything is up to isotopy,
Yeah, so which means I overcomplicated it. So it should be just GI, sorry for that. It's the same as,
wait a moment. So this relation is different from this relation you showed us for Jones towers.
no, I told you the same relation. I told you guys the same relation. The relation there was, I apologize that I made it a little bit too complicated. I confused it with the braid relation. But this is the relation from the Jones tower.
1 plus t squared. In the denominator.
Maybe this, okay, but maybe
this is the
this is for this K.
the position of exponents too.
Yeah, Okay, greater or equal
Yes,
3 was correct.
that's right.
Okay.
Okay.
Wait, I got lost. Let's say they.
There was a discussion.
Yes, I remember. Yeah, I started.
I think I wrote it incorrectly as C over 1 plus
T squared.
Well,
Ah. Okay. Okay.
I don't, yeah.
Okay.
But now so wait a second. So with these GIs, you have no coefficients. It's just GI.
Yeah.
But then,
That's the proof.
well, but then explain to me this. Imagine that J is exactly 2 apart from I.
Yeah.
All right. So then GJ commutes with GI,
Correct.
but it does not commute with GI plus 1.
Correct.
So I don't see, I have an equality here. And I take my GJ,
Yeah.
of course, commutes with the right hand side. When I go to the left hand side, well, I commute with GI, but how do I jump over GI plus 1?
So I is 1. J is 3.
Yes,
G1, G3.
yes,
So you can put G3 here.
yes,
This is G2.
yes.
So you have, okay, so there's another relation with minus here. Well, this is plus or minus. So G1, G3, G3 here, G2.
Yes,
Well, you have to use this relation. Well, it can be done. You just do it like Nike says, and you will be fine. I mean, we could probably write it, but
Why do you expect that this commutation with GI would be related to the commutation with GI plus 1? You are working in the algebra in the algebra when you have this relation. So this is GI simply. There is no contradiction.
I don't understand what you're saying.
You want to commute something which commutes with GI, you want to commute
Yes.
it with GI plus 1.
No, I just don't understand how it works because according to this presentation, G2 and G3 do not commute, right?
So what?
wait,
Well,
G2 and G3?
yes,
Correct, yes.
they do not commute.
So from these relations, you can generate many more relations.
Yeah.
Like, for instance, using the fact that something is commuting with GI.
Yeah. I don't think you have a contradiction. I think you have a question.
Yeah, I don't think it's a contradiction. It's for me, yeah, you're right, Adam. It's like a question. Of course, that formally speaking, you can say right side generating more relations, but it very often happens when you do rings that you generate so many more relations, you get something very trivial. Everything equals, zero. So that's very easy to happen in non-contact rings.
Although here we have a basis, it's non-trivial object.
I would like to see this calculation with G1, G2, G3. If possible.
Okay, but what do you mean? What kind of calculation would you like to do with it? Because it's already.
Like what is this extra relation generated by
This commutator with the G2. No, you meant G1, G2, G1.
Yeah, G1, G2, G1, yes.
G1.
Okay.
G1.
Yeah, okay.
Yes. Next, G3. Yes.
Exactly. Yes.
Is equal to G1, G3. Is equal to G1, G3 by this relation.
Yes, exactly.
Okay.
These two commutes, yes.
Yeah. By commutation relation, it is G1, G3, which is equal to G3, G1.
Exactly, yes.
Wait, G1, G3. Why?
Because I multiplied on both
And
sides.
then G1 and G3 are two
I think you want to write.
part.
That's what you want to write.
No. Forget about it.
Okay.
This is equal to G1, G3. G1, G3.
Yes,
Oh, I see. Okay.
Okay. Now it is equal to G3, G1.
correct, yes,
Okay.
correct.
Okay. And this is equal to G3, G1, G2, G1.
Exactly, yes,
Okay.
exactly.
This was George's question. So somehow for the price of
No, I don't know.
no.
I know, I didn't-
G1,
I know.
G2, G1.
I know.
G1, G2, G1. G2, G1. Okay.
Exactly. And now you can, basically what you obtain is now because you can now move G3 across G1. So you have G1, G2, G3.
Yes.
So you have that when sort of conjugated by G1.
So on the left hand side, put now G3 close to G2.
Yes.
Okay.
Okay, is equal to
Yeah.
G1, G2, G3, G1
Exactly. Exactly.
is on the right hand side, please write G1, G3, G2, G1.
Exactly. Yes. Exactly.
Wow, yeah, Piotr.
So if G1 was invertible, it would mean that G2 and G3 commute, but G1 is not invertible.
Exactly.
Okay.
That is exactly the relation I wanted to see. Yes. Yes. Yes.
Well, how do we know G1 is not invertible? Because it's an idempotent.
Because of that, almost an idempotent.
So yes, if you invert idempotents, you know that you are not going to get much.
Somehow, whatever the difference is between G2 and G3, it's killed by sandwiching it between G1. That's what I wanted to understand. And for me, it's not obvious.
And then this fancy John's tower came with a trace, even more fancy trace. And what's that? Well, this trace is just given by a closure. So if you have element of temporary leap algebra, consider n arcs closing it to link. Take the Kaufman bracket. It's a trace on temporary leap with certain numerical value if you specify A. And for this correspondence between A and Turayev's T, sorry, Johnson's T.
This T.
Yes, this T, which will make it it's a traced algebra isomorphic to trace algebra of Jones. Temporary leap algebra with trace. Okay, so
And the trace is normalized on the unit to be equal to 1.
yeah, okay, so it has to be normalized exactly to be 1.
Yeah, Bishan would always tell you that trace is normal.
Sorry, somehow I'm missing one thing here. R is general ring, but in the context of von Neumann algebra.
No, it's commutative.
So yes, so
Commutative, yes, but.
if you want to compare it to
Okay.
Johnson's
Yeah.
fraction, you have to take
Complex.
C and A, which will be will be related to T.
And what is the relation between A and T?
Give us some number as you explained.
I suspect exactly the same as before, that
Symbols.
T is A to 4 or minus 4.
Yeah, you wrote it, yes.
Yeah, you wrote it, yes.
A4 or A minus 4, yes.
So,
Okay.
all right, so this is some example of, this is an example of something which is like a scale model, although for scale models, we don't consider usually at the endpoints, at least not on this. But it already gives us a nice interpretation of temporary leap. I want to go back to scale models as I defined them in three-dimensional manifolds. And as I already mentioned, they are not easy to compute. You know, the generating set for a model is usually possible to find. Spanning set for a module, but finding precise relations, some sort of finite set of relations or minimal set of relations, that's a much harder thing to do. I will give you an example.
And what kind of information somehow this kind of module captures? So it is defined very similarly as singular homology, yes, where you consider all possible maps from singular simplices to the space and then divide by relation coming from the boundary.
Yeah.
Here I think that it is in somehow the same spirit. You take something which is huge, but also the set of relations is also huge.
You can think of it as a non-abelian homology of a manifold. And well, I'm going to actually come back to this question. This is a very good question.
Why non-abelian?
I'm going to come back to this question as well.
Additively is abelian, but you have the structure of a ring.
That's right.
Algebra.
I'm going to come back to this question as well. Very good. But I want to give you at least one example, so it's not completely abstract stuff. So this is I want to consider 2p plus 1 torus knot. It's a very simple knot, just a string of crossings, 1, 2, 3, 4. I need to have odd number because otherwise it will be a link. I need an odd number of crossings. So this is P equals 3. And then, I want to consider R3. I want to consider the complement of it. And I want to take the scale model of that. Okay, and it's going to be, it's going to have a basis of the form.
Sorry, but I'm really confused. What does it mean, M, N torus?
It's a name of a knot. A torus knot. That's one term.
Where is the torus?
Well, first of all, this knot looks like this. To answer your question, you can draw it on a torus. I can put the torus inside. I can relocate. If you like, I can relocate. I can relocate this part like this, and you can really draw it on a torus on a tube of a tire, if you have one.
But what if your tire is tubeless?
Then yeah, then it's harder. So its basis is the following. The following elements: m to power n, gamma to power k. Actually, it's good. Maybe I have a green. I don't know why I have a green, but it's good. This is a meridian. And m to power n means n meridians like that. So it's a formal notation. And then I want to have another loop. And another loop will be like this. And let's call it gamma. And then you will allow gammas. How many gammas? Up to k gammas, where k can be between 0 and p. So
N is what?
One is called meridian and gamma is not.
well, a little loop around the knot is always called meridian.
Right?
And gamma is some loop in three-dimensional space going like that.
There's two strings inside, right?
Sorry, N runs from 0 to infinity, or?
Yes, n goes from 0 to infinity. So forget about, well, forget about strictly less. Yeah, this loop is always called meridian. Forget about the fact that it's a torus knot. Forget this word. Okay, you have certain knots.
They are in R3.
And that's the basis. So I want to give you an example of something which was computed and was done by Bullock. Very concrete example.
Sorry, so this basis is just a countable set, so somehow this P doesn't play a role unless specifying some specific generators. But after all, you would get the same modules.
If you're only interested in isomorphism type of a model, then you're right. Isomorphism type of a model, then you're right. But you
would like
certainly
this presentation, yes?
Well, it's certainly used for presentation. Now you can distinguish different links living in complement of that using this basis.
Okay. So it is useful tool for
Yeah.
distinguishing things.
Yeah, we are interested more than just in isomorphism types of models. All right, but as I already said, and I don't mind saying it again because it's so true, it's very hard to compute scale models in general. If you give me, it's so easy to construct three-dimensional manifolds, say for by surgery, you ask me what's the scale model of it, most likely I will say no idea. And the mathematics, current mathematics, is unable to compute those things.
But we don't know about invariance of this kind model. For example, if two manifolds are, I don't know, homotopy equivalent, one could say something about this kind module.
If they are homeomorphic, then
Well, obviously, we know the answer. Homotopy equivalence is a very interesting question, but it's very unusual for three-dimensional manifolds to be homotopic but not homomorphic.
Well, like length spaces.
Yes, and that's pretty much the example. You can connect some of the same length space with something else. So I don't know the answer, but for length space, well, if you just look at isomorphism type, then they are the same. They are computed, those models are, by the way, computed for length spaces.
Adam, but I'm still confused by this relation. So how do I see in your picture that there's 2p plus 1, not 2p plus 7? Where do I see this number? For me, this notation, m comma n is confusing. Yeah, I have two numbers. I agree. You can choose them to be 2 and another one is 2p plus 1. Fine. But where do I see it in the picture?
Well, I basically want this number. If you don't like that, let's call it Q, but I want Q to be odd.
And Q signifies what? What is odd in the picture?
2 comma Q.
Yes.
It's not. It's a knot which has a Q crossings.
That's what I'm missing. Yeah, Q crossing. So yeah, you're right. So here you have what? Do you have 7 crossings or?
1,
Yes.
3, 4, 5. Oops.
That's why I'm completely confused.
You are justifiably confused.
And this 2 before the comma is this fact that you add just one extra string there. How do I see that? How would I distinguish 5 comma 2p plus 1 from 2 comma 2p plus 1?
PQ torus knot.
Oh, yeah. Now we are talking. Yeah. Yes.
Is the slope PQ curve or loop on torus, which sits in R3.
What is this P slash Q?
Okay, so so loops in a torus are classified by their slope, which must be rational.
Ah, I've got you now. Yes.
And if you take 2-5 loop on a torus, well, that's why I use this green, forgot about this part. I will be in trouble, I think, if I keep messing with this. But you can draw this knot on as a 2,5 loop on the torus in R3.
So this is the same, for example, 6,6p plus 3 torus knots, for example. Only the quotient plays a role, yes? The slope of this loop, yes?
No. So you're talking about knot which is 6,9. First of all, I for the theorem of Bullock, this needs to be a knot, and therefore P and Q should be coprime. This is classification of loops involves coprime P and Q.
No, so I mean 6 and 15 in your.
6,15 wouldn't be a slope because they're not coprime. That would suggest 3 loops.
Okay. I see. Coprime. Okay.
Yeah.
But only this quotient plays a role. It's a slope of this loop.
That's right.
Okay.
So it's yeah. I mean, basically, you can define torus knot for things which are not coprime, but that would mean that it was not just one loop, but several loops, and then you have a link. And Bullock, for whatever reason, only did it for knots. I suspect you can also do it for links.
That was exactly what I wanted to hear. Thank you.
Happy to.
You should get started with this because then I look at this 2,2p plus 1 and I have no idea what you're talking about.
Frankly, the name of the knots, how the name came to be, doesn't matter that much for the story, but of course it's good to have background.
Okay, and one more question. So as you explained what is PQ torus knot, so is it known, the form of this kind module of
No.
Well,
actually, I take it back. Actually, I should say no, indeed. So there is, I believe, paper, maybe by Marcia, maybe somebody else. And if they're on Zoom, I apologize. Yes, I believe that's. No, I take it back. It's unknown. No, it's unknown. I don't think it's known for this number other than 2.
Mhm.
All right.
Okay.
So I want to now, going back to this main thought, it's how to compute. Let's make things as easy as they can be. Okay, and let's try and understand the easiest case. And you know what? For that, we'll just do a new board. And what's the easiest case? Well, what do you suggest?
2, 3.
R3.
R3. Well, R3 with
Already, yes.
what we are going to do, we're going to take A to be declared to be plus minus 1 in some ring. How about that? Well, then we have this gain relation. But now you can, if you tilt your head, or if you rotate those pictures 90 degrees, then you get this rotation, this relation. Right? So, but those are equal. This is my bandy equal sign.
That's not the ribbon.
No. And so what does it say? Well, it says that
Minus. Yes.
for this value, yeah, you're right. It should be plus minus.
No, I mean that this equality sign is a blackboard minus. Yes. If blackboard is double.
2 lines, yes.
Oh, so this means that really, this means that for A equal plus minus 1.
Sorry, it shouldn't be if it's plus minus, then it's minus plus for the second one.
Well, this would be A and this would be A inverse.
Yeah. So it's the same.
Yeah, that's the same.
Yeah, you're right.
And so the conclusion is that we get a terrible not invariant. Because in this not invariant, we can change crossings of dots on X.
That kills the purpose of nothing.
That's right. And then what it means is that now it's the L is really links are considered up to homotopy. So let's keep studying this very trivial example as it seems. Now links we can consider up to homotopy because you can change crossings. And there is a benefit of that. This makes a model into an algebra. Because now we can define a product of 2 links to be a union of them. This joint union of them in M. I want to point out that in general, this product wouldn't make sense in a schema loop because there's no canonical disjoint union of 2 links, each of them considered up to isotopy in some exotic or some generic 3-dimensional manifold. Let's say you are in 3 torus. You know, how do you canonically place one isotope? We have one isotopy type, another isotopy type. How do you create a new isotopy type? There's no way to do it. On a side, so there's another multiplication which I will come back later. I don't know why it's so bad. Another multiplication. You can take actually any A and M to be surface S cross I. Well, if you have a thickened surface, then indeed you can multiply 2 links up to isotopy because you can always place one on the bottom and another one on the top. Stack them, yes. That's right. But it only works for thickened surfaces. This is very important. We'll come back to it. For now, we consider arbitrary manifold and this product. So this is not only an algebra, this extends linearly to the whole thing. Not only is an algebra, it's a commutative algebra. Of course, it doesn't matter, you know, L1 times L2 is L2 times L1. So you can ask, what kind of commutative algebra is that? And despite this seeming to be trivial, it's actually a non-trivial object. And even for the simplest ring in this case, which would be complex numbers. So there is a theorem. And the theorem is due to Bullock and Przybycki and myself, which says that this K model is isomorphic to the coordinate ring of the SL2C character variety of M. All right, now, what's that?
Sorry, and this isomorphism is independent of the choice of the sign?
Dependent.
Dependent.
Yes. I will talk about it, but maybe not yet. So the first things first, what's that? This is the space of all representations up to conjugation. Of pi1 of M, SL2C. So I shouldn't say, maybe erase this. Up to conjugation.
I mean, the fundamental proof of M.
Yes. So, okay, so and M is assumed to be connected here. So I'm going to explain this because it's a little bit not trivial, and I think it's interesting in its own, like for people even who don't care about knots and stuff. First of all, I should tell you this. This object is a variety in a sense of CERN. This thing, this coordinate ring, may have nilpotence. I'm going to explain this in a moment. So Bullock only proved it up to nilpotence.
What does it mean, up to nilpotence?
Yeah, I know. So exactly, this is a scheme. And so let's change gears.
Unreduced.
Let's change gears and talk about that. Because as I said, I think it may be interesting to people who don't even care about scale models. It's an important object in geometry, algebra, and physics. And to start it, I think I need to say something about algebraic geometry. So, in algebraic geometry, you have this duality between, on a basic level, affine algebraic sets, which are what? Which are zero Loci, zero sets of systems of polynomial equations in some affine space, C to N. Let's do everything over complex numbers. On one hand. On the other hand, yes, so this is just a zero set of some bunch of polynomials in Cn, P are polynomials in variable x1 up to xn. On the other hand, we have affine algebras. And these are C algebras on the complex numbers. What does it mean? It means finitely generated and commutative, of course, and reduced. And reduced means no non-zero nilpotence. And how does it work? Well, we associate with X.
Can you remind me this notation V of a bunch of polynomials?
is the zero set of those polynomials in Cn.
Solution set of the system.
That's right, the solution set of the
But it's the common zero of all of it.
That's right, yeah.
Okay, just double check.
And so you can, there's this notion of a regular function on X, which is just a restriction of polynomial function on Cn to X. Those regular functions, they form a ring, a C algebra, and this is the coordinate ring. Then, yeah, so it's not really very complicated. It's there's something called Nullstellensatz, which tells us exactly what it is. It is it's just polynomial ring quotiented by this ideal, except that it cannot have nilpotent elements because rings of functions have no nilpotent elements. The rings of C-valued functions have no nilpotent elements. So we take the nil radical of and then there's way back. So if you're an algebra, then you go back to an affine algebraic set by by a construction which is called spec M.
Wait, I'm confused by notation. Will you multiply out these polynomials?
No. Commas.
Comma. An idea.
They are generated by those polynomials. To go back, you use this construction, which is called spec M, maximum spectrum of A. And the details are maybe complicated, but to make it into an affine algebraic set. But as a set itself, it's pretty simple. It's a set of all maximal ideals. Ideals in A. And all right. Yeah, well, anyway, so this duality, the duality here between geometry and algebra, or certain part of algebra, affine algebras, is extremely useful for mathematics, as I think most of you know. And it's so useful that mathematicians or algebraic geometers want to have duality like that of more general nature, where you consider algebras here. So we want now a duality like this. By the way, this duality extends to duality of categories, yes? Category of affine algebraic sets with regular morphism between them, which one defines carefully, and affine C algebras with homomorphism between them. So one can extend
Wait,
this.
so what exactly is affine C algebra?
Sorry?
What exactly is affine C
It's
algebra?
finitely generated and reduced.
That's it.
Reduced means no nilpotents.
The spectrum is viewed as a topological space with Zariski topology, yes?
Correct, yes. But it's more than that because I didn't specify the affine structure for it, affine algebraic set structure for it, but it can be done.
So, Adam, it would help if you would put this finely generated reducing parentheses and write IE for finely generated reduced, because when I read it, affine algebras that are finely generated and reduced, and this is confusing.
I said it, but I didn't write it.
Yes.
By affine algebras, people understand finitely generated algebras, not necessarily reduced. So this reduction is modular nilpotence is based on the fact that on the left-hand side, the set of common zeros depends not on this ideal generated by P1 to Pk, but depends on the nil radical of this. Yes.
Yeah, although I must say.
So you can replace every ideal if you are interested in maximal ideals or in points of this. Okay, you can replace every ideal by its radical.
Yes, okay, that's right. Although just on a technical point, I think you mentioned that reduce is not part of affine.
Yes.
What I see in the definition is part of affine. But maybe there's some differences in literature. So what I want, or what people wanted, is to consider finitely generated category of finitely generated
And what's the relationship between this spec M of A and X?
It's a dual direction. So
Yes, so we go back to X.
you go in this way, yeah, in both ways. But if you go, yeah, in both ways, it will close to identity. It will become identity.
Okay, but where's that?
Inverse factor. So we want,
Naturally isomorphic to the identity.
Yeah.
yes, yeah. Yeah, as in the equivalence of categories.
Exactly, yes.
So
But there is a notion very strong of isomorphism of categories where you have exactly equality. It is artificial.
it is, but it's very rare, yes.
Yes, it's very rare, but
So I have to clarify this. On the left-hand side, you are not interested in sets. Otherwise, you would allow non-algebraic maps between sets of solutions of the system of polynomial equations. So you are interested in algebraic maps,
Mhm.
okay? So not only, yeah. So even morphisms must be algebraic.
So we want to extend it now to finally generated extension. So finitely generated.
So
Mutative algebra. So those, of course, also commutative. It can be done. And it's a little bit more technical. So this direction is that if you take any such algebra, okay. So I'm going to use now curl S. Let's see how it works. This is my fancy curl S. And you can do that. You can obtain certain object on this side. And this object on this side will be my uncurl S, which is an affine algebraic variety, and certain sheaf. And that sheaf is called regular functions.
sorry, you have written spec M, so do you consider a maximal or
Yes.
time ideas?
Only maximal.
Still maximal, yes?
Yes. Yes, I already wrote here maximal ideas. So that's fine. But I think I just do this now. Yes. So okay, we are not going to go into all technical details. We just want to get to my point. So there is an extension of this duality. Take any algebra, possibly with nilpotents. There's two arrows. This arrow looks like that. It's a affine algebraic set spec MA with certain sheaf of functions which we don't have to deal with. We don't need to know for what I want to tell you next.
there's a problem with this because usually on the level of ideals, the map between spaces of ideals is defined by the preimage of the ideal.
Exactly.
Yes, and the
So the problem is that the preimage of the maximal ideal is not necessarily maximal.
Correct.
So people were forced to use here
That's right.
spectrum of prime ideals.
That's right. But
And then you have equivalence of categories.
that is true. So
Yeah,
so maybe I don't want.
man,
Maybe I don't need to deal with equivalence of categories. But I have a duality of in limited sense that I'm going to associate to algebra spec M, which is this object of an algebraic set with a sheaf of regular functions. So there's a notion of what is a regular function, not only on this set, but on any open subset of it. There's some notion. I only want to deal with that. All right.
So the point is that now this sheaf can have stock with nilpotents.
Correct. So this sheaf is really a sheaf of functions. However, they are not C-valued functions, because if there were C-valued functions, there would be no nilpotents in this, no nilpotent elements in this sheaf. Okay. So
And this is the level of what? Affine schemes, yes?
So this is called a
Finite type.
this is called variety. Okay, so you can call this you can think of it as a special case of an algebraic scheme. This is also called variety.
No, but algebraic scheme is like a gluing different affine schemes, yes?
I'm not gluing anything, so it is also called
Very fine, everything.
variety or affine variety. Very good.
But these spectra are like local models for schemes.
Mm.
In the sense of CERN.
They are affine by definition.
So this is one way to call it. And so, yeah, we're not dealing with prime ideals. Let's just keep it like that. You know, it's I'm supposed to be precise here. Piotr asked me not to sweep anything under the carpet.
Oh, there's no carpet.
There's no carpet. But if I was allowed to sweep things under the carpet, I would just say this S means it's really a set. It's really this set. It's really an affine algebraic set with some extra information about nilpotence in A. Okay, this all given.
Yeah, I like.
All right, so we're done with algebraic geometry. Moving on. Let's talk about I guess group schemes. Why not? So let G be an algebraic group. And over C. All right, frankly, just for example, you know, it could be something very simple, like my favorite group is SLN. And this group,
I just non-compact.
sorry,
Non-compact.
I know. And yes, so, and they will be all affine. So none of them will be compact, unfortunately. But you can secretly maybe, yeah, right, I know you probably will secretly think about the SUN there somehow.
Complex algebraic groups which are compact are finite.
Yeah. And yes, yeah, and so yes, I'm not interested in the finite ones. And then it induces a functor from C algebras to groups. Oh, sorry. And you take C algebra A, and it induces G of A. Okay, so for example,
Yeah, yes.
for example, SLN makes sense for any A algebra. Algebras are commutative here again, commutative.
Oh,
These are irrational points of this algebraic group.
Yes. I hope you guys are okay with it.
Yeah.
So then take. So now let gamma be finitely generated. Frankly, right now it doesn't need to be finitely generated, but for the future group. And you know, if you want to study groups like that, I mean, they are very hard to study. Yes, the word problem in general is unsolvable. Isomorphism of groups is unsolvable. So we study them by representations, and it's natural to consider all representations of gamma into G. Such a thing is called representation variety. And I want to study it, and one way to do it is by looking at the universal G representation of gamma. So, definition. Think about the wording of this, the best wording. So, R of gamma G is the universal representation algebra rho sub u for universal is the universal representation.
So in fact, it's a scheme, representation scheme,
Yes.
parameterizing representations. And there is a universal representation algebra.
Yep, although I'm trying to use simpler words. And there is a universal representation. Or maybe G representation. If every representation into
If you write a G, you could add of gamma.
of gamma, yes. If for every C algebra, okay, and or I should say perhaps every C algebra, for every C algebra, every representation, and maybe just rho, going from gamma to
Commutativity is a standing assumption.
A, there is, yes, there is some homomorphism F from this universal representation ring, algebra to A, such that ST means such that my rho is really the universal rho composed with what happens when you apply G to F. So F induces.
You can write circle
Yes,
of the
please.
composition.
Yes.
Or you can draw a commutative diagram. It's a universal property.
Yes.
When you write C algebra, you mean a unit or commutative?
Yes.
There is unique, yes, unique F.
There's unique.
So right now, this is just a definition.
Yes,
No, there is a unique,
Unique.
the universal property.
This F should be unique, yes.
Yes, okay, very good. Very
It's
good.
a unique.
Exclamation mark.
I like it. There is exclamation mark. Yes, so this is just the definition, but now there will be theorem which says, yes, for every gamma and every G,
View
there are such things.
category theory is like initial object or like a terminal object. This property, this universal
This is an initial.
It's an
initial object in this space of,
A representations, or A rational representations.
okay.
And so you can expect the next theorem is
One more is from, okay, so it's initial.
It's obvious that this universal representation algebra exists.
Yes.
well, it exists. It exists
Logical.
and it is unique. Exclamation mark. And what does it mean? The R, which I mentioned, exists, is unique up to isomorphism. And this universal representation is unique up to something which is induced by the isomorphism of the R, of this R ring.
And easily constructed using generators and relations.
Yes, exactly. So that's what I want to do. I have a few minutes, so let's do it. So to avoid excessive formalism, this looks very abstract. Let's do something very practical. And so let's take gamma to be generated by two elements. By x, comma y, and G be my favorite group, which is GL. No,
SL.
they made mistake with my favorite group, SL2C.
So gamma
You
is,
can always change your mind.
but not necessarily free. Gamma is not necessarily.
No.
Okay.
Generated. Then what? Well, what is this rep thing? Well, then, did I say rep? I said R. Sorry, R gamma G. Well, what's going to be? Well, it's going to be a ring, a polynomial algebra on 8 variables. Okay, so I'm trying to now distinguish, but this is like a simple x and y, and this is a curly x and y, which corresponds to the simple one. Okay, these are elements of the group, these are variables. And it has to be quotiented by something, by some ideal I. And where this is the smallest ideal, this I, the smallest ideal, such that what? Such that this homomorphism rho u from gamma to SL2 comma R exists. Oh, well, what do I mean by that? Well, it will send, of course, X to matrix Xij. And it should send Y to matrix Yij. And so, yeah, so now we can consider some example of this. So, for example, when gamma is just free group on X and Y, then we have only two polynomials to consider, yes? That's crazy. We have only two polynomials to consider. Well, we just need to make sure that the determinant of each of those matrices is 1. The same for Y. But yeah, this is the minimal number of relations which you have to put in I for this to make sense. And this gives you the universal representation. Every representation now of free group into SL2C somehow will be induced by homomorphism, which is really induced from this ring to C.
And if you have more relations in your group, you have to include those relations in the definition of I, yes?
Correct. So for example, now if gamma is just Z2, then this R, this I will have additional relations. How many additional relations? Well, you can say 4 relations, because you need to ensure that the 4 entries of this matrix coincide with the 4 entries to this matrix. Yes, I mean, basically you have to multiply this. What's that? One entry. So one entry of XY. So, okay, maybe there's not enough board here, but I think you guys know what I mean here.
Commutativity.
Well, yes, we need to make sure that one entry of this matrix is the same as for this one, and the same with other entries. And each of them will lead to a polynomial in x's and y's, which has to be satisfied. Frankly, do we need 4 relations? We don't, because they have the same trace. So it's enough to ensure that 3 of the 4 partitions are the same. I mean, yeah.
Sorry, maybe just one more question. So somehow I think that in your argument, in your example, you are using the fact that you have 2 generators and also you are representing everything on SL2.
Yes.
This 2 is the same. What happens if you have more generators in your gamma and still you would?
Well, then I would call it Z per generator, and I will have Zij here.
Yep.
Yes.
And then if you want 5 here, then you have Ij to consider from 1 to 5.
Okay, and that's all. So no more problems. Yes.
Well, yeah, no more problems. More complicated formula for the determinant.
If there are
One.
there's a finite number of generators, it's almost like this.
Okay.
So I think it's a good time to stop and we are past time.
Okay, thank you so much. Any quick questions?
So next time you are going to speak about this action of G on itself by conjugation.
That's right. This will define character variety.
The quotient.
Yes, we'll talk about a quotient to consider, which will be something called GIT quotient, because set theory quotient is not adequate. And then I will continue. So basically it will mean that schema modules can be thought as what? Well, for A equal plus or minus 1, it's really coordinating of character variety. For generic A, they're like Q deformations. You know, the A is like Q. So there are Q deformations or quantizations in some sense of character varieties. And so I will continue on this theme.
Excellent.
So GIT will give you obviously that the quotient, the algebra of the quotient is finally generated.
Correct.
And what is the argument for non-existence of nilpotence?
There may be nilpotence.
Yeah, but if you have this finite generated group, and if gamma is T1 M, why this algebra has no nilpotence?
Oh, I never said that. It may have nilpotence.
But you proved with Przytecki that it has no nilpotence.
For surfaces, you mean?
It's for surfaces. Yeah. Where M is equal to surface cross the interval. Okay. So, but do you have examples of such representation spaces or character spaces with nilpotence for manifolds different from this product type?
I do.
Perfect.
It must be different because, of course, there are no nilpotence there. But
Yeah, of course.
so, first of all, there are some existential theorems. And yeah, I'm not kind of doing spoiling the next time. But
Next time,
Yeah.
okay, perfect.
But I also believe I have some very concrete example.
Adam,
No question.
anybody from Zoom? Okay, I don't see any raised hand.
But I have a question. I have another question.
Say,
Okay, yeah.
I have another question. Could you come back to these two products? One coming from the stacking and another by taking the sum and taking the value of A equal to plus minus one. Yeah, yeah. So if you have these two multiplications.
What do you mean two multiplications?
There are two.
This is for A equal.
These are two different multiplications.
So there are two reasons for this kind module to be an algebra. One is sticking to A equal to plus minus one, and another one is specific choice of M. Yes, so for different reason.
Yeah, yeah. So what if you take A equal to plus minus one and you assume that M is of this product type?
Well, I get the character variety of surface.
Yeah, but is there a relation between these two multiplications?
So for A equal one, this is generally non-commutative multiplication, but
Okay.
A equal plus minus one is actually the same. It is commutative because you can pass crosses. So
So this is the same algebra.
the same.
Perfect. Thank you.
Okay, maybe I would have one question,
So
sorry.
this is a deformation of this commutative algebra. If you change the parameter A from this particular value to some, let's say, for instance, three formal parameter, you obtain a deformation.
Correct.
Perfect.
Yes, so I have a question related to that. So this choice of A could be thought as you explained, as taking some deformation, but is it enough to consider one universal ring and then deformation in this one ring is enough to know the behavior of this game modules for the others?
Yeah, this is what I mentioned before. This was this bookkeeping here that
Yes.
any ring
Yeah.
Any ring is really, any ring of the type we want with specified invertible A is really a model over this ring. So it's enough to compute it for this ring. But the other side of the token is, it's also the hardest to compute it for this ring.
Are we going to speak about the Poisson structure behind this deformation?
I can talk about it.
So this is due to Goldman, if I remember.
That's right.
Very good.
Adam, so where is the question?
It was already asked about this deformation in universal ring. Is it enough to consider deformation in one particular ring? And the answer is yes. If we take R to be Z of.
One ring to rule them all. Okay.
Exactly.
Okay, so now let me wind it up. I stop the recording and we resume on Friday.